This is problem 11169 on page 711. At the bottom of a loop in the vertical plane, an airplane has a horizontal velocity of 315 miles an hour and is speeding up at a rate of 10 feet per second squared. The radius of curvature of the loop is a mile. The plane is being tracked by radar at O. What are the recorded values of R dot, R double dot, theta double dot, and, well, theta dot and theta double dot for this instance? All right. Let me sketch the problem. So I put the radius of curvature up here where I could see it. And down 1 mile is the plane. I'm going to call it P. As far as we're concerned, by comparison to that mile, the plane is a point. The vector R from the station on the ground, let me just draw the station, a little building, I guess, with an antenna of some kind. The vector from that point O there, put it there. The vector from O to the point P is the vector R that we're interested in. We're interested in R dot, R double dot. How fast is this vector changing length, and what's its acceleration rate? What about the angle of theta? How quickly is it changing? By the way, theta is measured this way. If the plane's moving that way, you tell me, is theta increasing or decreasing? Well, at this point, it looks like it's decreasing, but be careful because remember this plane is following a curved path. Now it's at the bottom of the curve, so just depending on, I think at this point, yeah, we've got a straight line velocity, so certainly in this instant, theta has to be decreasing, but it's possible the plane will come around and eventually the vector will have to point back up, right? But for right now, I agree. I think that theta dot will be a negative thing. And then theta double dot was also requested. Now at this point, the velocity of the plane is 315 miles per hour. I went ahead and converted that and found that to be 462 feet per second. That's what I computed. Hopefully it's right. The plane we know is also off the ground 18 feet. Let me pull it off over here. Not 18, excuse me. That'd be low flying. 1,800 feet. There we go. Not a mile, but getting close to the same order of magnitude. And then, well, actually that would be the same order of magnitude. And then the distance horizontally from O over to P is 2,400 feet, about half a mile, roughly. Okay. Now, the reason I like this problem is that it combines normal and tangential components with radial transverse components, because if you think about it, we already know quite a lot about the plane's motion. We know that this plane is moving on, it is moving on a circle, isn't it? They told us the radius of the circle. Oh, I forgot one thing. They also told us the acceleration of the plane. In fact, they gave us the tangential acceleration. How do I know it's the tangential and not the normal acceleration? It's because they said the speed is changing at a rate of 10 feet per second. You see? So this is tangential acceleration, 10 feet per second squared. And they told us that 5280 feet is the radius of curvature of this plane. Okay? For the path that it's on. So couldn't I calculate the normal acceleration of the plane? I think I could. The normal acceleration would just be the square of the tangential velocity divided by the radius of curvature. So 462 feet per second squared divided by 5280 feet would give me the normal acceleration. In fact, that number comes out to 40.425 feet per second squared. Is this plane doing something interesting? This normal acceleration is over 32.2 feet per second squared. What does that tell you about the weight of the people inside of it? They feel like they're twice as heavy as they really are, don't they? In fact, a little more, because this is more than a g of acceleration. I don't know what kind of plane this is, but If it's a commercial airliner, they're gonna be in trouble when they land. Pilot will be. Anyway, so there's the normal acceleration. We've got the tangent, so we actually already know everything about the acceleration of point P, don't we? We've got the tangential and the normal acceleration. As a matter of fact, if we were to draw some coordinate axes, we would say that there is a normal direction here, and, if I can move that velocity over just a little bit, a tangential direction here. Tangent to the path, just a horizontal line to the right. Okay. But notice that the coordinates for the radial transverse coordinate system look like this. The radial direction continues from O to P. I'm sorry, it's not quite straight. It should be along the line. And how about E theta, or the transverse direction? Well, that continues the theta direction, you see, in the positive rotation direction of theta. Okay. Any questions so far? All right. So could I write, for example, vector R, could I write it down right now? Sure. Vector R goes from O to P. So that is simply 2400 in the I direction. Oh, by the way, we're going to use an XY coordinate system as well, because why not? Let's just bring everybody to the party. Okay. 2400 I plus 1800 J, and these are, of course, P. So there's the vector R, but I can't take this and say, well, what's R dot? Well, these are both constants, so R dot's 0. No, that doesn't make any sense, right? We know that this point has some velocity and some acceleration, and so we have to somehow deal with that. So let's go ahead, though, at the time, while we have the chance, let's go ahead and find theta. Why not? We're going to need that position information as well. So theta would be equal to, let's see. Well, I define theta a little bit differently. Help me out here. Let's see if what I defined is the same. So theta would be the inverse tangent of what? Well, we need y, which will be this dimension, 1800, over x, 2400. Okay? And yeah, that's what I did. So this comes out to about 36.8699 degrees. I didn't know how many decimal places I need, so I just grabbed 4. And by the way, while we're at it, why not calculate the magnitude of R? Root 2400 squared plus 1800 squared, square root. Pythagorean's theorem gives us 3,000 feet. They gave us a nice round number for the length of R. So this is what we would have referred to before as R when we use the velocity and acceleration equations. Okay? In fact, to make sure you understand that, go back and look at the radial transverse acceleration velocity equations. Page 695, equations 1142 and 1143. When we just have a lowercase r there, it's this r we're talking about. It's not a vector r. In this book, vectors are bold, whereas non-vector scalars are not bold. Now, I've got a little bit of a problem here because I've got r expressed in ij format. I would rather have r expressed in ERE theta terms. Now, you should already know what the answer is. You should be able to tell me how to express r with what I've given you here in terms of, well, ER and E theta. Does the vector r have any E theta component, or the transverse component? No, that's the definition of ER. It lies in the same direction as r. E theta is perpendicular to it, so there is no transverse component to r. It's saying that this is just perpendicular, right? That's all it says. What about ER? How long is r along the direction ER? We just calculated it. 3,000 feet. So basically, I could have written it this way. I could have simply said 3,000 ER feet. By the way, anytime you express the vector R, it will only have ER components, okay? It will never have E theta components. All right? Let's see, let me see if I need to write that down or not. I think we're okay. Oh, well, in case you look at my work a little bit later, I got a confession to make. I forgot about this fact. I wasn't thinking about that. I was thinking, oh, well, I can calculate this angle theta. In fact, I called it alpha if you look at my sheet. I should have called it theta. I can calculate this angle, and if I calculate that angle, I can actually perform a coordinate transformation to go from the XY coordinate frame to the ER E theta coordinate frame. And you know, I think I made a mistake here. Because theta dot, yeah, you know what? I made a mistake in my solution. I'm going to have you help me with this. I drew E theta in the wrong direction. E theta should be in this direction. And I messed up. So we'll have to go through and correct my work. But it shouldn't be too bad. So there's ER E theta. And we know that this angle is just theta, isn't it? Okay. So how would I transform these? In other words, if I have a unit vector I and a unit vector j, which is what I had right here, I was thinking, well, how do I transform I into components ER E theta? Well, that's not too bad. I is 1 unit long, so it's longer than the projection of ER, so it would be something like this. So it would give me quite a bit of ER, right? And I need some negative E theta to finish off I. Does that make sense? If I add ER plus part of E theta, that would give me I. Another way to look at this is as follows. So this is I. How would I represent I in terms of those two? Well, this side would be cosine of theta, ER. Okay. But I also need to add to that sine of theta, E theta. Okay. You know what? I feel like I've got that backwards. Let me think for a second. It made sense when I did it. Let me think about it for a second. So I is along this direction. I think I may have this backwards. I'm going to write I in terms of ER. Well, let's see if it would make sense. It's not too bad. We've got the value of theta. So tell me, what is cosine of 36.8699? Let's make sure I got that right. I've got a number on my sheet, but now I'm really questioning myself. So grab your calculators. Take cosine of 36.8699 degrees. What do you get? That's what I got. How about sine of 36.8699? I got 0.6. Did I get it right? Sorry. Let's just ask the question, if we take 80% of ER and add to it 60% of E theta, would we end up with I? Well, we can draw that, that's not too bad. ER, 80% of it is going to be something about like, maybe that much, right? And if we were to add to it, oh, I had E theta the other way, so this would be a negative sign, but that's the only change there. So if we add 60%, let's see, that's 1, I think 60% is going to be about there. So yeah, I think we would end up with, yeah, and that makes sense because basically we have a 0.8 0.6 and therefore a 1 on this side, right? Because this is a, you recognize this as a 3, 4, 5 triangle, right? So yeah, that does work. I was just thinking of my triangle backwards a second ago. But yeah, so that should be correct. Now I had a plus sign here because I had my transverse direction wrong. So this equation should be just fine. And anywhere I have I, like here, I can replace it with this. Okay? On the other hand, what about j? What about this unit vector? Well, for that one, I'm going to need 80%, or in other words, sine, I'm going to need sine theta, let me get this right, it's got to be opposite. I'm going to need cosine theta, there we go, to get this length of e theta. And I do need the positive because I need that direction. I'm trying to make up j. And I will also need a positive component from ER, but that component would be the sine component. And that should represent j. Okay? We can check that one as well. If I take, remember sine was what, 60% and cosine was 80%? If I take 80% of e theta, that puts me about there. Take 60% of ER, that should give me a vector j that has length 1. And here's the right triangle. Any questions about all this? We're doing okay. All right. Have you guys seen coordinate transformations before or not? Okay. Don't remember it? Yes, no, maybe? Kind of fuzzy. So all I'm trying to do here is express this vector in terms of e theta ER. Let me show you what happens. So like I said, I wasn't thinking and I went through all this work. This will be useful for other things later. Okay? In fact, it showed me I messed up. But anyway, so if we write 2400 I, but I is cos theta ER minus sine theta e theta, plus 1800 j, but j is sine theta ER, bar, plus cosine theta e theta. We know that cosine of theta is 0.8, sine theta is 0.6. So now we should be able to represent R, that's what this is, as, let's see, 2400. Tell you what, do me a favor, what's 80% of 2400? See if I can figure it out first. 200 away, 40, 80, 1920. Is that right? Yes. And then 60% would be half 1200 plus 240, so 1440. Am I thinking right there as well? Okay. Plus, we need 60% of 1800, so if we take half, 900 plus 180, 1080. ER. Plus 80%, so what I'm going to do is take 360 from this, right, 1440. Okay. Notice what happens. The transverse components exactly cancel. And what we're left with is 1920 plus 1080. You might want to take a guess as to how much that is. You don't have to calculate it. 3,000, isn't it? So this works. This coordinate transformation works. This allows me to go from ij to r theta. I can use this. I can substitute these in anywhere I have an I and a j, and I'll have the vector in terms of r and theta. That'll be really handy because look, expressing the velocity of the plane in terms of x and y is pretty straightforward. So now I will be able to express the velocity of the plane in terms of ER theta. That'd be kind of nice. Same thing with the acceleration. I've got the total acceleration in normal tangential components, which by the way, it just so happens that the normal direction is exactly the same as j, and the tangential direction is exactly the same as x. So these equations will work as well. In other words, this is the same thing, I is the same thing as the tangential direction, and j is the same thing as the normal direction. So any place I've got a normal tangential, like here with these accelerations and velocities, I can use these transformations to get into r theta instead. It's just expressing it with different unit vectors. That's all we're doing. Okay? So, let's do that. Let's take care of that next. If we've got, where am I going to do this? I guess we'll just do it here. Let's write down, in fact, I'm going to ask you for your help because I don't trust my sheet. Like I said, I use the opposite theta, the opposite transverse direction. That was wrong. I shouldn't have done that. So with these corrected transformations, let's see what we can do. So the velocity vector is pretty simple. It's 462 feet per second in the I direction, isn't it? Right now the plane's at the bottom of its arc, and so it's just got horizontal velocity. So this I could be represented as cos theta ER, it's supposed to be a C, minus sine theta E theta. Okay? We already know what cosine of theta is. In fact, let's write it down so I don't forget it. Cos theta in this case was what, 80%, and sine theta was 60%? Right? So, rather than doing it here, let's just plug it in. Let's use the board. 462 times 0.8 ER minus 0.6 E theta. So I need 80% of 462, if you guys wouldn't mind doing that, because I'll probably make a mistake if I do that in my head. I'll try it anyway.
369.6.
Thank you. 369.6 ER. How about 60% of 462?
277.2.
Thank you. And these are both feet per second. So there's the velocity vector expressed in terms of ER and E theta, right? But wait a second. Isn't the velocity always, I don't know, let's go look it up. Equation 1142. It's R dot ER plus R theta dot E theta. What does that tell you? Doesn't that tell you that this is our R dot? So we've answered the first question. What is R dot? It's 369.6 feet per second. Okay, does that make sense? We're sort of working things a little bit backwards here. And R theta dot is 277.2. Well, negative 277.2. Could we figure out theta dot from this? Yes. We already know the magnitude of R. It's 3,000 feet. Right? So what this tells us, I want to erase these transformations. What this tells us is negative 277.2 equals 3,000 theta dot. Now be careful because I wrote it this way without units because I'm trying to avoid going off the screen on the camera. But we know that these are feet per second, and the other side, the 3,000, are feet. So when we divide out the feet, what units will we have for theta dot? Radians per second, exactly. So take negative 277.2, divide it by 3,000, what do you get? And that'll be theta dot in radians per second. I'll write it down over here. So what is negative 277.2 over 3,000?
Negative is 0.0924.
Okay. Negative 0.0924 radians per second. Where did the radians come from? They're a dimensionless unit that we can use. If you don't understand that, talk to me about it sometime. I'll try to explain it to you. I try to understand it myself. I just go with it now. Okay? Now, when I did this before, because I had my transverse axis reversed, I ended up with a positive number. But it makes more sense that theta dot is going that way, right? That it's going down like we said originally. It's not going this way. It's not coming up. Okay? All right. Let's not forget that R, so let me put it here. R is equal to 3,000. And of course, theta, the position information, is 36.8699 degrees, though I don't think we really need theta anymore. The reason I did that is because I need this space. I'm going to erase this up here. Because we need some space to work with acceleration. Can we write down the total acceleration of the plane as a vector? Yes, help me out. Help me do that. Tell me what to write down. You see the accelerations right here. 10 feet per second squared and 40.425 feet per second squared. Trying to write down the acceleration as a vector.
I and J coordinates,
Yeah, we'll use I and J, that's fine.
so 10I, plus 41.5J.
Plus 40.425J, right? Now, of course, we could have said that this is the, the tangential direction, and this is the normal direction, but like I said, they're the same thing, right? They point in the same direction. The tangential and I direction are both this way unit vectors. Normal and J direction are both up that way. Okay, so take your pick, it doesn't really matter. So there's the acceleration written in either the normal tangential coordinate system or the Cartesian coordinate system. So what we're going to do now is, of course, transform it into the radial transverse coordinate system. So let's do that. So ET, or I, is cos theta. In fact, you know what? Let's save ourselves some time. That's 0.8. This is 0.6. 0.6. 0.8. So 80% ER minus 60% E theta, transverse direction, plus, from here, 40.425 E, that would be En, or also J. It's like an N. Let me try again. But En or J is 60% of ER, plus then 80% of E theta. Okay? This math is easy. 8 ER minus 6 E theta. Give me a little bit of help with this if you don't mind. 40.425 times 60% is how much? 34.255. Pardon?
24.255.
Thank you. ER. How about 80% of E theta?
32.34.
So now, if we combine the radial components, 8 and 24 are 32. And then take 6 away from 32, would be what, 26? I've neglected to write my units, but of course they are feet per second squared throughout. So now we've got the acceleration in terms of ER and E theta. Why would we bother with that? Well, because of equation 1146. So this is the same thing as R double dot minus R dot, no, R theta dot squared ER plus R theta double dot plus 2 R dot theta dot in the transverse direction. So what we've just discovered is that R double dot minus R theta dot squared is equal to 32.255, isn't it? Just those two pieces. Okay. Also, R theta double dot plus 2 r dot theta dot equals what?
26.34.
26.34. Of course, feet per second squared in both cases. Okay. Could I solve now for r double dot and theta double dot? Sure. I've got r, I've got theta dot, I've got r dot, I've got theta dot, I've got r. So I will be able to solve for r double dot from the first question, or the first equation, theta double dot from the second. So let's see. We've got answers over here, so we don't need this anymore. So r double dot would be equal to 32.255 plus r theta dot squared. 32, notice I'm dropping my units. I know that these are feet per second squared, I'll make a note of it, but I think everything will come out all right. Because r I know is 3,000 feet. And theta dot squared will give me radians per second squared, which is an angular acceleration of sorts. So negative 0. I'm sorry I'm off the video, I'm just writing down theta dot and then I'm going to square it. 0.0924 radians per second quantity squared. So you can say, well, it's radians squared per second squared. Okay, that's fine, whatever, radians are dimensionless. So feet per second squared, everything will work out. So if you would, go ahead and calculate this for me. Now you should get the same answer I got for r dot because we're having to square this term. And my term, of course, had opposite sign, SIGN. So I think from this, what we'll get is 57.87, but verify that for me if you would, please. .87 feet per second squared. I guess I could put boxes around these as well since they are also legitimately answers. Did I hit buttons on my calculator okay?
Yep.
Okay. So now let's solve from here for theta double dot. Theta double dot would be the 26.34 minus 2 r dot theta dot, just moving this term to the other side, all divided by r. Okay. So let's see, some space. Theta double dot equals 26.34 feet per second squared minus 2. R dot we know is 369.6 feet per second. Theta dot is negative 0.09, again I'll be off the screen, 24 radians per second, all divided by r, which is 3,000 feet. Let's check units. We have feet, 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 so the feet are gone. We've got second squared, so sure enough, theta double dot will be radians per second squared, which is what we expect. Now my answer is going to be wrong because I had a positive number here, and so I would have subtracted this term, and in fact I should have added. So if you don't mind telling me theta double dot, I'd appreciate it.
.032.
0.032. Or 0.0315.
They don't really mean a whole lot to you, but there they are. Why would we care about this? Oh, before I go into this discussion, any questions on the example problem? Why would we care about this? Well, there's a project I've wanted to do for a long time now. You guys know about the International Space Station, right? You know it's eventually going to be decommissioned. I don't remember when. It seems like they keep saying they're going to shut it off and then they keep extending its life, so who knows? Did you know you can actually build something, just a device that will point always to wherever it is, even pointing down through the earth? Okay, I think it's based on Arduino, and so you can build this device and build a mechatronic system that always points in the general direction or pretty close to where the space station is. You can also build a telescope for fairly low price. It's fairly high power. It takes patience and a little bit of elbow grease, but you can do it. It's called a Dobson telescope. Here's what I'd like to do. Have you heard of a Pixie Cam? Last piece of the puzzle. Pixie Cams are fairly old now, but a Pixie Cam is just it used to be about a $60 or $70 smart camera that could track a whole bunch of balls bouncing around at one time. So if you had a 2D image or video of balls bouncing, it would recognize the colors and track the motion of each ball, which is pretty cool. So here's the idea. What about if we use that original Arduino-based system to point towards the International Space Station? Obviously that's kind of like this, isn't it? Right, with radio transverse coordinates. And then point our Pixie Cam through a low power telescope at that area of the sky. So basically mounted on the end of this pointer would be the Pixie Cam to look up in the sky. Now the International Space Station should be visible most times. It should be a dot that kind of looks like a star or something, okay? And maybe there's a little bit of magnification with the telescope so we could pick out that white dot, okay? So the Pixie Cam tells us where it is, and of course the Arduino is automatically pointing in the general direction of the space station. The Pixie Cam tells us where in its field of view it's located, the space station is located, and then we use a mechatronic system to aim much more precisely with a much more powerful telescope. Maybe we could see the International Space Station fly overhead, maybe see the solar panels or something, So that would be related to this, and there's a whole lot of this math in behind it, because think about it, the rate of rotation of the arm pointing towards the space station, it's Arduino based. Yeah, okay, that part's already been solved, but somebody had to deal with this to figure out how quickly to move the arm in order to get it to point at the space station, you see? And how quickly they had to accelerate, and all those things would be involved in this. So if I can figure out a way to make that happen, hopefully we'll do that as a project this semester. That'd be cool.